Okay, hope you guys are doing well. I'm just going to go ahead and get started here just to try to make this video as short as possible. So last class I ended with going over this kind of graph thingy, and I'm going to really quickly go back over it one last time, kind of try to explain it in a different way. I think it was a little bit difficult to conceptualize for some people because it is kind of a weird concept, so I'm just going to kind of talk about this here. So once again, we have the graph of our function, our normal function here, and then we have the graph of the derivative, right? So this red straight line is just, the graph of the derivative as a function. And basically what that means is that if I look at any point on my graph, for example, right here, I look at the tangent line like this. It's my best work at a tangent line, and I want to know what is the slope of this tangent line. Okay, that's my question here. What is the slope of this orange line, right? All I have to do is look at my red graph, okay, right? So the x value of this point, right, is at x equals 1. So I just have to look on my red graph, where is that point? So that's right here, that red dot. And what is the y value of that point? Well, that is 6, right? And so what that tells me is that the slope of this function, or the slope of this tangent line, is 6 at this point. Okay, and I can do that for anywhere else. So if I went over to like this point, right, also have a tangent line there. Okay, and I want to know what's the slope of this tangent line. Okay, all I have to do is look at that same x value, right? So the point directly below it on the derivative, this value right here, this point, and I have to look at what is the y value. Well, it's 2, okay, and that tells me that the slope at that point is 2, right? So that's what this red graph of the derivative of the function tells me, right? At every single point, I want to know what is the slope of the tangent line of the function, right? And I could do it really anywhere at any point, it doesn't matter, right? And I want to know what are the slopes of these lines, right? All I have to do is look at what is the value of the derivative, this red line, directly below it, right? So what are these y values? Okay, and that'll tell me the slope of these tangent lines, right? So that's all there is to it, really. And so if we move on to these notes, I know that I maybe have already filled these out, but in case I haven't, so f of x has a local maximum at x equals what? So that's going to be this point up here. That's our local max, right? And so that's at x equals 4. Okay, right? And what I'm going to kind of make a note here is that f goes from increasing to decreasing, right? That's basically what a local maximum is, right? So if we look at this point, everywhere to the left of this blue point, the function is increasing, right? The black function is increasing. Anywhere to the right of it, it's decreasing, right? And that's what makes it a local maximum. Okay, and then on the graph of f prime of x, the derivative, we're going to note that f prime of 4 is equal to 0. Okay, and basically what that means is that f prime, okay, I'm going to write f prime of x, this is f of x, goes from positive to negative, right? Because that's exactly what the derivative tells us, is that when the derivative goes from positive to negative, right? So if I look at this point on the derivative, right, everything over here to the left is positive, everything over here to the right is negative. Okay, and that is exactly why on our actual function, everything to the left is increasing and everything to the right is decreasing, right? So positive increasing, negative decreasing. That's kind of the relationship here between the function and the derivative. Okay, and then the slope of f of x at x equals 1 is, well, that's going to be f prime of 1, right? That's always what the slope of the function at the x value is, right? You just plug that x value into the derivative, right? And so what's f prime of 1? Well, that is this point right here, which is 6. Okay, so f prime of 1 is equal to 6. And this last little note is since f prime of x is decreasing, its derivative, f double prime of x, must be negative. I'm just going to write that here. And when f prime of x is negative, right, we know what this means. This means that our actual function f of x is concave down, right? That's exactly what the second derivative rule is, right? If f prime of a is less than 0 or negative, then f of x is concave down. Okay. Right, and then we just have some notes here. This is going to be a little bit of a lot to write in this small space, but I'm just going to write it. This is basically just all the relationships between the function, its derivative, and its second derivative, right? And so f prime of x is greater than 0 if and only if f double prime of x, is greater than 0 if and only if f prime of x, so this is my first little bullet point, okay, is increasing. Okay, right, and that is also true, okay, if and only if, let me see, f of x is concave up, right, we know that, and this is also if, actually, excuse me, I'm going to write the slope of f of x is increasing. Okay, as we move left to right and we look at the graph, the slope of the function is increasing. Okay, and then the second one here is that f double prime of x is less than 0 if and only if f prime of x is decreasing. Okay, that's if and only if f of x is concave down. And that's if and only if the slope of f of x is decreasing. Okay. Right, and so the reason that we want to write these things down is it helps us just understand, once again, the relationship between the function, its derivative, and its second derivative. Okay, and then the the last thing we have for this section is just this example where we're looking at these graphs, and we want to know, right, we have a function, okay, where the slope and the function itself decrease, okay, right, so we have two things. One is that our function is decreasing, and the slope of the function is also decreasing. Okay, and you might read that and be like, what is that talking about? That's the same thing, but it's not the same thing, and I'm going to kind of try to explain that here by doing this problem. Okay, so what this question is asking is that we have a function that's decreasing and the slope of the function is also decreasing. And the question is, which of these four functions is that? Okay, so these four functions are behaving in different ways. Which one of them is both decreasing and its slope is decreasing as we go from left to right? Okay, and so let's just look at the first one. The function is decreasing. So which of these four functions is decreasing? Well, what it means to be decreasing is if you imagine yourself walking on the function, walking on the blue curve from left to right, you're kind of sliding down, like sliding down a hill or going down a roller coaster, something like that, right? So if I look at both B and C, the two ones in the middle, on both of those, if we go from left to right, we're going up, right? We're increasing there. Okay, so it's neither of those. Okay, right, so we have A and D left. Okay, so on both of these, you know, from left to right, we are decreasing, right? This is like you're sliding down a hill. This is also like you're sliding down a hill. It just looks a little bit different, okay? So the question is now, on which of these is the slope of the function decreasing? Okay, well, the way that I would go about this is if I look at 2 points here, okay, so we're just going to look at A first. I'm going to look at 2 points on the graph, and I'm going to draw the tangent lines. Okay, there's this tangent line. Okay, did my best job there. Okay, I'm going to do the same thing for D, so let's just pick a point over here, a point down here. I'll draw the tangent line. Let me redo that. And then, okay. And my question now is, as I go from left to right, so I look at this point first and this tangent line first, right? So this one has a pretty steep slope, okay? It looks like it could be like -7, -10, something like that, right? It's very steep going downwards. Whereas if I move to the right, okay, this next one is a lot flatter. It's closer to just being like a horizontal line, right? So the slope is going from a really steep downwards to a little bit more mild, still going downwards, but almost closer to being flat, right? Which means the slope is increasing, right? I'm just going to write this as an example, but for this one, we could have like the slope is, right, like -7, whereas this one, it could just be like, m is equal to -1/2 or something like that, right? So as we go from this slope to this slope, right, are we increasing or decreasing? Well, we're increasing the slope, right? So let's look at the other one. Okay, so on this tangent line, right, this slope looks more like, this could be something like -1/2, right? I'm just taking a guess, but that's what I'm going to predict it is. Whereas on this one is a lot steeper. This could be like m equals -7, right? So as we go from left to right, from this slope to this slope, right, we're actually decreasing in slope. It's getting, more negative, I guess is the best way to describe it. And that's what we're looking for, right? The slope of the function is decreasing, which is what's happening here. Okay, so I'll just fill that in, right? So it's function D. Okay, and that's all we have for this section. So I'm going to move on to 2.3. Okay, and we're just going to start this one. We're not going to get through the entire thing. We'll save the rest for Friday, but let's get started here. So essentially, these local maximums and local minimums are something that we've been talking about a little bit lately in class, and this section is going to be about how to find those when you're given a function. Okay, so the first terms it gives here are critical values and critical points. Okay, and essentially, right, we kind of talked about how, let me go back to this one, right? Remember, so we were given all these facts about our function, and then our job was to, draw a sketch of that function. Well, whenever we were given something like f prime of 3 is equal to 0, so f prime of something is equal to 0 specifically, we knew that we had that horizontal tangent line at that point, right? Same thing for this one. We were given that f of 2 or f prime of 2 is equal to 0 and f prime of 6 is equal to 0. And that's how we knew we had these horizontal tangent lines. Okay. And what we noticed is that every time we had one of these horizontal tangent lines, it was either a local min or a local max, right? So this one down here was a local min, and this was a local max, right? And so it turns out that is exactly how we find local minimums and local maximums, right? Is we look for places where the derivative is equal to 0. Okay, right? So we have something called the first derivative test for this, right? So if f prime of a is equal to 0, okay, and f prime of x changes from positive to negative at x equals a, right? So a is just some value, then f of x has a local maximum at x equals a. So what this is talking about is that I'm going to draw a picture of what this graph will generally look like, right? So we have a local maximum. So hopefully you guys remember, generally it looks like this. Okay, so there's our point up there. There's our local max. And the x value is a. Okay, so this could be any number, 3, 5, -2, whatever you want, okay? But this is what a local max looks like, okay? Hopefully we know that, right? And what this is saying is that f prime of x changes from positive to negative at that point. So I'm going to kind of make a little chart here to explain what's going on here. So I've got a few, it's kind of a table. So here's f of x, and then here's f prime of x. So we're looking at the x value a, okay? And at f of x, or f of x whenever x is equal to a, right, we have a local max. That's what this is saying. And then when we have a local max, what's happening with the derivative? Well, up here, it says f prime of a is equal to 0, right? So it's equal to 0 there, okay? And when we have a local max, what's happening before that local max, right? What is the function doing in this area? Well, it is increasing. So I'm going to draw this arrow. That's kind of like going upwards, right? For like an increasing slope, I guess. Whereas to the right of that point, right, we're decreasing. So it's like this. Okay, so what happens with the function is that it increases, hits a local max, and then decreases. Okay, and then what's going on with the derivative? Well, we know that when a function is increasing, the derivative is positive, right? And then we know that when the function is decreasing, the derivative is negative. Okay, and so basically what this is saying is that if you want to know, right, is my point a local max or a local min, I have to test before that local max, right? So in this area, is my derivative positive or is it negative, right? Same thing over here. Is it positive or is it negative? Okay, and the reason that I say that is because for a local minimum, right, what's going on with the local minimum? That's more something like this. Okay, so here's our point at x equals a, right? And then, yeah, that's what a local minimum looks like, kind of just the opposite of a local maximum. And so I'm going to draw that same table here. So here's my x value, f of x, and f prime of x, right? And so when my x value is a, okay, well, what's happening with my function? I have a local minimum, right? So what happens before a local minimum in this region? Okay, so my function is decreasing, right? And then what happens over here? My function is increasing, right? I can erase these. Okay, and then what's happening with the derivative? Once again, when my function is decreasing, right, the derivative is negative. Whereas when it's increasing, the derivative is positive. Okay, and then at the local min, once again, derivative is 0. Right, and so that's exactly how we know if our point, right, where the derivative is 0, right, we have that horizontal tangent line, right, we want to know, is that a local min or a local max? And that's why we examine what's going on with the derivative, right, around that point. Is it negative and then positive, or is it positive and then negative? Okay, right, and then we're going to do some practical examples of this, okay? And so, oh, and we have this one last little example. This is basically saying that if we have a horizontal tangent line, right, our f prime of a is equal to 0, but f prime of x does not change sign at x equals a. So basically what that's saying is if it went from, I'm going to erase this for just a second, imagine that the derivative went from positive to positive, right? Or imagine it went from negative to negative, right? In other words, what would be happening here? That would be like my function is increasing, it hits a local min, and then it's increasing again, right? Or other way around, my function's decreasing, hits a local min, and then it's decreasing again, right? So, if we want to know what this, sorry, I'm going to draw this back on here. That's negative, that's positive. What does this look like? That's when you have stuff like this, right? So here's my point at A, where my horizontal tangent line is, my tangent line is horizontal, right? The derivative is 0, but I have something like this where it's increasing, hits that point, but then just increases again, right? So obviously this is not a local max or a local min, okay? And that's kind of what this is saying, is that if you find that your derivative is positive over here and positive over here, then there's no local min or no local max, okay? Right, so for our first example is we have this function f of x equals negative 1/3 x cubed plus x squared minus 12. And it comes out and just tells us one local maximum and one local minimum point, right? So it has a local max and a local min. The question is find these points using the first derivative test. Okay, so luckily, this is one of those problems where there's kind of just a process you can go through, okay, to figure this out, right? So the first step, find the derivative of your function, right? So there's our function up there. Our derivative is going to be f prime of x equals negative 1/3, and then bring the 3 down, x squared, right? And then plus 2x, okay, because the 12 goes away. Right, so I'll simplify. This is negative x squared plus 2x, right? Because the 3 on the bottom, 3 on the top goes away. Okay, so there's our derivative. Our second step is sorry, my handwriting has not been great, but we want to set this derivative equal to 0 and then solve for x, right? So I take my negative x squared plus 2x equals 0, right? Now I want to solve this equation for x. So this one isn't entirely obvious what you want to do here. Technically, you could do the quadratic formula for this one, but something that I notice is that both of these terms have an x in them, right? And so I can pull out an x, so I'm going to pull out a positive x, right? So I'll factor it out. So the first term becomes a negative x, and this second term becomes a plus 2. Right, so that's how I'm just going to factor that out. You can, check that this is how you factor it by just distributing, foiling this out. Okay, and then if we remember, right, whenever you have two things, this thing and this thing, multiplied together equal to 0, that means that you can just take each of them individually and set them equal to 0. So x is equal to 0, and negative x plus 2 is equal to 0. Okay, and then this gives us negative x is equal to negative 2. Which gives us x is equal to 2. Okay. So we have x is equal to 0 and x is equal to 2. Okay, so these are our critical values. Okay, essentially, these are the places, the x values, right, where we plug them into the derivative and it's equal to 0. Okay, so these are the x values where I have that horizontal tangent line, that red horizontal tangent line that we've been drawing. Okay, and then my third step, I'm going to kind of draw it over here so I'm not wasting space. Okay, so step 3, okay, plug plug the critical values into the original function to find the critical points, right? So essentially we know where these x values are, right, where we have these horizontal tangent lines, but we don't know what the y values are. We don't know like where they are on the graph, So I want to take each one and plug it into the function. So our first one is x equals 0, so I'll plug 0 into f. So that is, there's our function up there. So this is going to be negative 1/3 times 0 cubed plus 0 squared minus 12. Okay, so this is going to be 0 plus 0 minus 12, which is equal to negative 12. So our first critical point is at 0, comma, negative 12. Okay, and then our other one is at 2, right? This 0 and this 2, that's these guys, right, are critical values. Okay, so I'm going to plug that in. Negative 1/3 times 2 cubed plus 2 squared minus 12. So this is going to be negative 1/3 times 8 plus 4 minus 12. And this is going to be at, let's do this math fast in my head. It's going to be negative 8/3 plus 12/3 minus 36/3. So minus 8/3 minus 24/3. So this is going to be minus 32/3. Sorry, I just didn't want to have to write anything else out. Oh, excuse me, over 3. Right, you can check that with the calculator if you want. Okay, so that tells us that our other critical point is 2 comma negative 32/3. So these are our critical points. Okay, so these are the points on the graph where we might have a local min or a local max. So what we have to do now is use our first derivative test, okay, that we just learned above, to figure out which one is a local max and which one's a local min. Excuse me. Okay, is the first derivative test. Okay, so what I want to do here, okay, right, if you need to pause, replay this step that I'm about to do as many times as you want, that's totally fine, because there might be something that you miss, but this is the way that I personally do it, the way that I think is easiest to visualize. Okay, so what I want to do is draw this number line. I'm going to make it a little bit larger. Okay, so essentially this is like the x-axis, right? I'm just looking at a specific part of the x-axis. And I want to look at my critical values. So remember, these are these guys, 0 and 2, those x values. I want to plot those, okay, on the x-axis. I need to make sure that I put them in order as well. I have to do 0 and then 2, right? If I put 2 here and 0 here, okay, then the first derivative test actually won't work. It'll give me a wrong answer. So I need to make sure I put 0 and then 2, right, in ascending order. Okay, and then what I'm going to do is that in each of these spaces, right, to the left of 0, I'm just going to pick a number. I'm going to go with -1, right? Try to do a pretty simple number, easy to work with. And then I'm going to pick a number between 0 and 2. So I'll just go with 1. Okay, and then a number to the right of 2. So I'll pick 3. Okay, and I'm going to put a box around it, right? And so now what I want to do is take each of these values, these test values, okay, and I'm going to plug them into the first derivative. Okay, so f prime of -1 is equal to, well, our derivative is this, -x² plus 2x. Okay, so -1 squared plus 2 times -1, which is -1 minus 2, so -3. Okay, and what I want to acknowledge here, okay, is that this is negative. Okay, right? And so I'm just going to put a negative sign here, okay, above this region, right? And then I'm going to look at my next value. Okay, so 1, I'm going to plug that into the derivative. So f prime of 1, that is -1 squared plus 2 times 1, which is equal to -1 plus 2, which is equal to 1. Okay, this is positive. Okay, so I'm going to put like a plus there. Right, and then my last one, f prime of 3, so -3 squared plus 2 times 3, so -9 plus 6, which is -3, so this is once again negative. So I'm going to put a minus there. Okay. So, right, what is the purpose of this? What are these minuses and pluses about, right? So I'm going to go back, okay, to my first derivative test, all my notes I took here. And these pluses and minuses, right? What are these talking about? These are talking about the value of the derivative. Well, what happens when the derivative is positive, right? That means that our function is increasing. That's what this blue arrow means. And then when the derivative is negative, that means our function is decreasing, this other blue arrow that's going down, right? And so what this tells me, what I just found here, well, over here on the left, this negative means that my function is decreasing, right? The derivative is negative, so my function is going down like this, okay? And then what about the middle region, that plus? Well, a plus means that my function is increasing, okay? And then this last region, I have a negative, so that means my function is decreasing. Okay, I'm gonna make that a little bit better. Right? And so now I look at each of these points, right? I look at my critical point here. So what's happening to the left of it? It's decreasing. And then what's happening to the right? It's increasing. So what does that mean? I have a local min, right? That's exactly what's happening at a local min, is that you're decreasing, you hit that point, that local min, and then you start increasing again, right? That's exactly what we have right here, right? Decreasing, and then we hit the local min, and then we start increasing again. Okay, so this is a local min, right? And then what about this point? Okay, well, we're increasing, and then we hit that point at 2, and then we start decreasing again, right? And that's a local max, right? Same thing that's happening up here, right? For a local max, we're increasing, hit the local max, and then start decreasing again. Okay, so that's how we know that that's a local max. All right, so we kind of create this diagram to help us visualize what's happening with the function, right? It's sort of like a graph, but we're just getting like the bare bones, of what the graph of this function looks like, right? And so we have a local min at this critical value or critical point at 0, right? So we have a local min at, and it wants you to put the point, right, the actual point itself, so not just 0. We want to put 0 comma negative 12, right, because that's what we found up here. So local min at 0, negative 12, right, and then we also have this local max. Okay, so we have a local max at, where is that? It's this point, 2 comma negative 32 over 3. Right? And so the cool thing here is that here's our function, right? This f of x equals negative 1/3 x cubed plus x squared minus 12. And if we wanted to know where the local mins and the local maxes are for this function, we could just graph it and look at it, But what this is showing us is that we can use the derivative of the function to just figure out where those local mins and local maxes are without even looking at the graph, right? And we figured out where they are, okay? And then you can, graph this, go to Desmos, and put this in to confirm that these are the points that have local mins and local maxes, okay? So, yeah, this is definitely not the end of this section, but I'm going to stop it here, and then on Friday we should be able to finish it off. If you have any questions, then feel free to email me. Hope the video was helpful, and hope you guys are staying warm. Yeah, have a good day.